So I want to get into, after doing some of those, very specific examples in the last video, I want to get into some more, I don't know, philosophical ideas, I guess. So the idea behind a basis is that it's a collection of vectors that's linearly independent and spans the entire space. And so let me just draw an example in R2. One of our vectors could look like this. Another one could look like that. And they're not just rescalings of one another, right? They point in different directions. So they are going to be linearly independent, and they are going to form a basis for R2. However, think about the context that we've had in this entire class about how the dot product can inform various things about relationships of vectors. In particular, they always tell you how much, the dot product always tells you how much two vectors agree with one another. Right, so if I were to blow this picture up a little bit, right, so I've got my two vectors that look like this. And, if I project one of them onto the other, it doesn't really matter which one I use, but if I project one of them onto the other, you can see that the projection of one of the vectors onto the other is pretty substantial, right? There is a lot of overlap. That's what this is telling us. There's a huge amount of overlap. They basically point in almost the same direction. So what this means from like a signal processing kind of idea, a data analysis kind of idea, is that there is a ton of redundancy, in a sense, built into this basis. All right, they don't point in the same direction, so they are still a basis. However, they point in very similar directions. All right, so there's a lot of overlap. The projection of one vector onto the other in this basis is pretty substantial. So let's refine this idea of a basis a little bit farther, and let's introduce basically an idea of not having too much overlap. Right, and if you think about it, the way that you can minimize the length of this red projection, right? How can you make this red projection as short as possible? So if you just sort of imagine, let me keep the bottom vector the same, and if we just sort of imagine that this other vector points in a more drastically different direction, well then if you look at the length of the projection, it's significantly shorter than it was. And, if I do the exact same thing again, so let me draw yet another picture here, and I have them point still farther apart, well, then the projection vector is pretty darn short. And, think for a second about what relationship these vectors should share to each other. How should they actually relate to one another in order to make that red projection vector as short as humanly possible. And I think it's not too hard to see that to make that projection as short as possible, you should actually have orthogonal vectors. Right? If they are orthogonal, then the projection itself is the zero vector. Right? The orthogonal projection would just be the zero vector if they are already orthogonal to one another. And this is effectively saying that orthogonal basis vectors completely disagree with one another, in the sense that they have nothing in common. So from a redundancy point of view, these there is no redundancy. This is a zero redundancy kind of system. Right? The information that's contained in one of the basis vectors is completely different in every way from the information that's contained in the other. All right, so this is the first refinement that I want to make of this notion of a basis that we have. So what we want to do here is have the idea of an orthogonal basis. All right, so an orthogonal basis is exactly what it sounds like. We're going to say that the collection B, which is the collection of vectors v1 through vn, is an orthogonal basis if B, of course, is a basis to begin with, right? It's got to be a basis first. And Vi is orthogonal to Vj whenever I is not equal to j. All right, so it's groups of vectors which are what we would say is pairwise orthogonal. Okay, so in the case of a two-dimensional picture, that would be precisely this image right here. Right, we would have exactly two vectors if the space is two-dimensional. We would have exactly two vectors in the basis, and they would be orthogonal to one another. And there is a little exercise that you can check here. If a collection of non-zero vectors, right? So I'm always talking about non-zero vectors here. I'm never going to include the zero vector in one of these collections because that would just be silly. So if this collection is an orthogonal collection, well, let's think about what that would actually mean, right? In terms of this this picture in the purple box here, these two vectors are orthogonal to one another. And think about what the important aspects of a basis are. It's got to span the entire space, and it has to be linearly independent. And things are linearly independent if they can't be written as scalar multiples or linear combinations of each other. And if you think about it, just intuitively speaking, it's hard to be more linearly independent than being orthogonal. All right, so if you are orthogonal, you point in, basically as different a direction as is possible from the other vector. And so the idea here is that if you have an orthogonal collection, right, so if V1 through Vn is orthogonal, then it is also linearly independent. All right, so you can prove this. And the idea for the proof is exactly what I just said, intuitively speaking, that orthogonality is like a really strong kind of linear independence. Right? It's where you're linearly independent to the point that you are completely pointing in opposite, or not opposite, but different directions, as different can be from all the other vectors in the collection. All right, so I'll leave that as an exercise for you. And to sort of get you started at the very beginning of how this should go, you would want to begin. Right, you're trying to show linear independence, and so you want to begin by supposing that if C1 V1 through added up through Cn Vn is equal to 0. Right, this is always how we begin linear independence proofs, or checking linear independence, whatever you want to call it. If this linear combination of the v's is equal to 0, you want to show, WTS, want to show, that all of the c's must be equal to 0 themselves. And all you know is that the collection is orthogonal. So what you're going to do is use this orthogonality idea and what orthogonality tells you about the dot product, right? This tells you that, say, Vi dotted with Vj will be 0 if I is not equal to j. Use this dot product idea combined with your only supposition right? Your hypothesis, which is that this linear combination adds up to 0. And using the dot product with this thing in the blue box here, you'll be able to conclude this, that all the coefficients individually must be zeros. All right, so I will leave that as an exercise for you. Now, the most important part about this is always, how do these extra conditions and extra properties that we're throwing onto these things, how do they actually help us? So, the idea here is that orthogonality is a very strong property. It should be able to give us some more information, or some better information, or maybe some faster information. So we should be able to do things more quickly, maybe, than we could without orthogonality. All right, so the idea behind any basis, all right, why these bases are important, is so that you can take any vector in your space and you can decompose it into the coefficients in terms of these other vectors. All right, so basically what you're doing is you're figuring out how much a given vector from the space points in the direction of these various basis vectors. And so it gives you a way of breaking it down into like atoms. That's what a basis really is. It's like all of the atoms that make up a given thing. When they're put together in the right way, it creates whatever object you're trying to look at. So it gives you a set of building blocks to build up your vectors in your space. And so really the most important thing about a basis is the fact that any vector in the space can be written in terms of a linear combination of those basis vectors. All right, so if B is an orthogonal basis, and again, we're always going to be saying that B is some set V1 through Vn of vectors. If this is an orthogonal basis, what we really want to do is to know how to compute the coefficients in any linear combination. So basically any vector decomposition that we want to know about. All right, so how do we compute coefficients for an arbitrary vector? V, I guess you would call it. We've got the Vn's, the V1 through Vn, so maybe I'll call it U in our space. And again, we know that this is even possible because this thing is a basis, which means that it spans the entire space. All right, so we know this can be done because B spans the whole space, just by the definition of what it means to be a basis. All right, so this means that we would be able to find C's, C1 and C2, and so on, that would make these basis vectors add up, or in a linear combination, add up to this vector U that we're starting with in our space. So we know this can be done because it's a basis. And the first thing I really want to emphasize here is that this is really the why we care about bases for vector spaces. It's about figuring out the decomposition of any given vector U into the linear combination in terms of the basis vectors. And really what that boils down to is figuring out these coefficients. All right, these coefficients tell you, in a sense, how much of U points in the direction of V1, for instance. how much of u points in the direction of v2, and so on and so forth. So this is really the most important part about bases, is being able to figure out these coefficients, because the coefficients tell you how to deconstruct a vector into its basis components, or if you know just the coefficients, how to build that vector back up from the basis vectors by adding them up in this linear combination to reconstruct the original vector u. Okay, so this is the general idea, and so what we want to know here is, how do we actually compute these coefficients? Because any vector in the space can be decomposed into either deconstructed or reconstructed using the coefficients. The entire question, as far as we're concerned, becomes, how do you actually calculate these coefficients? So, we're supposing that we've got an orthogonal basis. So, what I'm going to do here is to use that to our advantage. I know I've got an orthogonal basis. That means that they're pairwise orthogonal. So v1 is orthogonal to v2, v1 is orthogonal to v3, v1 is orthogonal to all the other v's, and you know, v2 is orthogonal to v3, v2 is orthogonal to v4, v37 is orthogonal to v38, and so on, right? They're all pairwise orthogonal. So we're going to use that to our advantage. What we're going to do is think about how we can isolate C1 from this decomposition. To isolate C1, what I want to do is figure out a way to make C2, V2, all the way up through Cn, Vn. I want to make those disappear. Right? This is the idea, so that I'm only left with C1, V1. And if I can make those other coefficients disappear, that will tell me what value C1 has to have. All right? So if you think about this, I have a very effective way of making all of this stuff disappear. And it's by using the fact that I know v1 is orthogonal to v2, v3, v4, every other vector inside of this, what's being underlined with this blue bracket here. v1 is orthogonal to all of those because I'm starting with an orthogonal basis. So what this means is that if I take this decomposition that I know has to exist because we have a basis here, which means it spans the whole space, which means it's hypothetically possible to find these C's that would do this for us. If I take this decomposition and I dot both sides of that equal sign by v1, right? So I'm going to take dotted by v1 over there, and I'm going to take C1, and then here I'm going to have v1 dotted with v1 plus C2, v2 dotted with v1, and so on up through Cn, vn dotted with v1. And now something really great happens, because I know that each one of these, right, for instance here, v2 is orthogonal to v1 because it's an orthogonal basis. So that whole term is 0, right? The dot product of any two orthogonal vectors is 0. And similarly here, vn is also orthogonal to v1 because it's an orthogonal basis. So that's also 0. Everything in the dot dot dots is a similar situation. They all dot to 0 because of orthogonality. So what this tells me is that u dotted with v1 is equal to c1 v1 dotted with v1. And now I'm trying to solve for c1 here. So let's just go ahead and divide by v1 dot v1. What this tells me is that c1 has to be equal to u dotted with v1 over v1 dotted with v1. And what this first of all, this formula should look familiar, right? This is a thing that should absolutely look familiar to you at this stage of the course. And what this tells us is that if we put this back into our formula for how to reconstruct, right, this formula up here, this formula for how to reconstruct u, this arbitrary vector, from the v's, well, what it says is that u is going to be equal to c1, and now we have a formula for c1. This is u dot v1 over v1 dot v1 times v1 plus c2 v2 all the way up through cn vn, right? We just don't know what those are yet. We haven't done the work to figure out what c2 through cn are. We've only done the work at the beginning here to figure out what c1 is. All right, and I'm just plugging that in right there. Now, this thing, what is that? This is something we know and love in this class. What is that thing? Pause the video, take a few seconds, think about this. This is something very specific that we have looked at so many times so far in this class. So hopefully, if you thought about it, this thing is precisely the projection onto V1 of u. It's the orthogonal projection onto the first basis vector of this arbitrary vector that you started with in space. And I mean, this is awesome, right? This tells you exactly how to calculate the coefficient, first of all, because the coefficient is this coefficient that goes in front of V1 in the projection formula. And the part of u that points in the direction of V1 is precisely the projection onto V1 of u. Just like you thought it maybe should be, right? If you tried to think about these, the idea of what a basis is really trying to tell you, you're really asking how much u points in the direction of these various vectors, v1, v2 through vn. So what we just found is that u can be written as a projection onto v1 plus all of this other stuff that we have yet to figure out formulas for. But it should not be surprising to figure out that, let's just do C2 for instance. Right, if we start with the fact that u is supposed to be equal to C1 V1, and now we know what C1 is because we just calculated it, but I'm just going to write it as C1 to save space, plus C2 V2 plus all the way up through Cn Vn. Do the exact same thing we just did, right? Let's go ahead and dot on both sides by V2 now. And again, the 2 is because I'm trying to isolate C2. Right, so u dot V2. Everything is going to cancel here, except, right, so I'm going to have V1 dot V2 plus C2 V2 dot V2 plus up through Cn Vn dot V2. And again, because this is an orthogonal basis, all of these things that are dots between vectors that have different indices, so V1 dotted with a V2 for instance, that's going to zero out because of orthogonality. And I'm just going to be left with that one term. And so the formula for C2 here is going to be exactly the same kind of thing that we just saw with C1. Right? It's u2.v2 over v2.v2. And this is going to be true for all of the CNs, right? Or CIs, whatever you want to call them. Every single one of the C's is going to have an analogous formula to this. And so this gives us our first big thing, which I would say is worth calling a theorem. And the theorem is as follows. If B, which is V1 through Vn, is an orthogonal basis, then we can calculate the coefficients of any vector in the space, right? So for any u in the space. U is equal to the following. You're going to have U dotted with V1 over V1 dot V1 in the direction of V1 plus, and the same formula is going to be true for all of them. U dot Vn over Vn dot Vn in the direction of Vn. In other words, U is equal to a sum of projections. All right, so this is really the projection onto V1 of U plus the projection onto V2 of U added up through the projection onto Vn of U. Right? It's just a sum of orthogonal projections. And the fact that we have an orthogonal basis is why we can use orthogonal projections to tell us how much of U, the vector, points in the direction of all of these different basis vectors. It's really pretty cool. I think this is one of the coolest things from linear algebra. And it gets a little bit cooler, because there is something that's even nicer than just being orthogonal. In particular, if you look down here, right, what are these denominators in our projection formula? Right, so let me just grab one of them. V1 dotted with V1. This is really the same as the magnitude of V1 squared. Right, so in every one of these denominators, we're having to effectively, to calculate these coefficients in our basis decomposition, we are going to have to, in calculating the coefficients, we're going to have to divide by the magnitude of our basis vector squared. So, wouldn't it be nice if we didn't have to do that, right? If we didn't have to worry about that. So, what value of the magnitude of V1, or Vi, I'll say, for any of them, what magnitude of that value, or what value of that magnitude is, and here I'll put this in quotes, because what does this mean? Which value for the magnitude is best, in a sense? And best, of course, doesn't mean anything. Most efficient, most convenient, fastest, these are what I mean when I say best. And so this is what I will address in the next video.